In this lecture, I'd like to go through two more example problems about reaction diagrams that focus on endothermic and exothermic and the differences between those. So I have two reactions here. Hopefully you've tried to do this on your own and drawn an energy diagram for each or a reaction diagram. I'm going to start with endothermic. I've got nitrogen and oxygen gas combining to form NO gas. I forgot the G. So as this reaction occurs, it is going to get colder to the touch. This means it's grabbing energy from around it and using that energy or heat to drive the reaction forward. That means that our heat in this is really going to be a reactant. So if we're going to be absorbing heat to be able to form our products, that means our product is at a higher energy level than our reactants. And so we can represent that on our reaction diagram by putting our reactants at a lower energy. So that's going to be our nitrogen and our oxygen, and our products at a higher energy, or 2NO. And this difference right here between them, that is what we call enthalpy. That is the amount of energy or the amount of heat that needs to be absorbed by the reaction to be able to form those products. It's going to have a positive value because the energy of the products is higher than that of the reactants. And it really represents heat being absorbed by the reaction. And so just this difference right here is the fundamental piece of the reaction diagram, showing the difference between the reactant and product energies. We can kind of complete this by putting in uh, a peak of it that represents the transition state or the activation barrier or activation energy. For this reaction to occur, we need to break bonds and form bonds. And at this transition state, it's the most unstable part of the reaction. It's at its highest energy to maintain it. And it's where all of our bonds are half broken and half formed. So it's like the hardest part of a race. And the amount of energy, the difference between that transition point and where we start in terms of energy with our reactants, that is our activation energy. The activation energy isn't a value we can determine from knowing if it's endothermic or exothermic. It's something you would have to study by modeling instead, which obviously is beyond the scope of this course. But it represents that amount of energy that's required for this reaction to even occur. If our reactants don't have enough energy to overcome that transition state energy, we won't ever form our products on the other side of it. All right, let's look at an exothermic reaction now. This is sulfur dioxide and oxygen forming sulfur trioxide. And so this one is exothermic. That means it's going to have energy released as the reaction occurs. It's going to give off heat, kind of like a campfire would. And so that means that our heat will actually be a product of the reaction. So I can think about that as a product. And what it means is that when we form our product, it is at a lower energy than our reactant was. And so we don't need as much energy to create that product that we use to create the reactant. And that excess energy just dissipates out into the surroundings, heating them up. So that means that our reactants are going to start at a higher energy than our products. So our reactants of sulfur dioxide and oxygen will be at a higher energy than our sulfur trioxide. And that difference in energy, again, that is my enthalpy. And it's going to have a negative value this time because those product energies are lower than our reactant energies. And it's saying that, well, basically, we're releasing heat into the surroundings. Again, just like our endothermic reaction, for this to take place, my reactants have to have enough energy to overcome a transition state. And that transition state isn't something that we can predict from our enthalpy, but we can still include it and draw it in like this. So here's our transition state where everything is half broken and half formed. And our activation energy is right here. It's always going to be the difference between the energy of the reactants and the transition state, that peak. And so this is what our exothermic reaction diagram will look like.